And I know some of this is a little bit of a rehash from Thursday, but there are things that I know I was rushing and I want to spend a little more time being careful and diplomatic. So for those of you who are, I guess, are still not calculus students and are having to take all of your calculus from me, building a motion equation is something that takes practice and isn't obvious. In our spring mass oscillator, we are considering a middle point. Again, I'm saying that this object is moving with some velocity this direction. It was displaced originally some max amplitude. We are somewhere in the middle of the object's motion. All we know is that we have a boundary condition, and that boundary condition was at a t equals 0, the velocity was 0. We released it from rest. But after that, it's being governed by a restoring force. Now, I want to take a few minutes to talk a little more about restoring forces. We have one type of restoring force in our kind of arsenal of material that we've learned, that Hooke's law is a restoring force. Restoring forces have two specific parameters. The first is that a restoring force is always in the opposite direction of a displacement. Okay, that's the first thing you have to know about a restoring force. It's always in the opposite direction of a displacement. Second, a restoring force is in some way proportional to the displacement. So the more you displace something, the bigger your restoring force gets. Hooke's law is a linear restoring force, but there are other restoring forces out there that are not linear. The result we generate today is based on a linear restoring force. That's why we're studying it, because it happens a lot in nature. But there are plenty of restoring forces that aren't linear. But still, the most important part of this function is that negative sign. That tells you one specific thing, that the force is in the opposite direction of the displacement. And as I'm going to start here, your job in this regard is really just to follow along. We're never going to have to do the calculus that I'm going to describe here. So you don't need to be able to do the calculus, but you need to be able to place certain variables in certain positions at the end. You have to recognize the pattern that we're going to create. The spring mass oscillator is the model. So when we find another oscillator, we try to make that oscillator fit this model. There's going to be two important variables here. One of them is going to be K. We want to see if the new system that we're going to find, say the pendulum, we want to see if it can be modeled as a constant times a displacement. So that's what we're starting with. Hooke's law is a constant times a displacement. The value of K may be the spring constant for the spring, but if any force is proportional to displacement, whatever you get for that proportionality constant, it becomes the K in our answer. So we're trying to build a model for how we can apply it to other simple harmonic oscillators. We have to start someplace, and remember, when you're asked to build a motion equation, you have to start by generally finding a differential equation, because we know we have differentials that are related to the motion variables. So these are the differentials that we know that are related to the motion variables. So we're generally looking for an equation that has acceleration or velocity in it already, so that we can create a differential equation. In this case, I've told you already where to start. You always should start with Newton's second law, because it has acceleration built in and it brings inertia into your problem. So when we start building our motion equation, that's where you start. Net force equals ma, because A is a differential. When we've done these problems before, we've usually gotten forces that are dependent on velocity. And velocity is a first differential right here. This one's going to be different because it's not going to be based on velocity, it's going to be based on position. That's what makes this one different, one that we've never done before. So we place our one force in here, minus kx, and that equals ma. This is not yet our differential equation. We are creating our differential equation from here. And this is what we were doing on Thursday. The problem is that we want to take and replace A with a differential. The problem is our first replacement gives us dv dt, but our other variable is x and not v, which is why we have to do it twice. This is the derivative of a derivative. It is the second derivative. And we have symbology here. The symbology that we use is a little bit cumbersome. It shows that there's a two d's there, so they just say, okay, we'll say d squared and put the x there, and then there's two dt's on the bottom, so they say dt squared. This is just symbology. There's nothing squared here. These are symbols. It means a second, I can't spell, Mr. Sheldon, be better. A second order differential, or taking the second derivative. That's what this symbology means. Obviously, a 3 would be the third, and a 4th would be the 4th. It's just symbology. All of you who are going to college, colleges expect you to know other things. You should know that there is something called dot notation. It's a shorthand for derivatives with respect to t, specifically with respect to t. So this is velocity, x dot. It is the first derivative with respect to t. It's a shorthand notation that makes for a cleaner look, and colleges expect that you've been taught this. Second derivative would be acceleration. X double dot is the second derivative with respect to t. Dot notation is taught everywhere else, but apparently Florida doesn't teach dot notation. But most students going to college from other places have been exposed to dot notation, and professors often expect that you've seen dot notation before. It won't be your first year professors. It's going to be the ones like 2 or 3 years in. They're going to suddenly think you got taught this and you never did. So it's just something to put in the back of your mind. It's a shorthand. It's to make writing this stuff out a little bit easier. You'll probably learn it in differential equations because they use dot notation quite a bit. It is generally reserved for derivatives with respect to time, but it's not exclusively for that. But this is pretty common in most circles in science. I'm not going to use it. I'm going to use the cumbersome one, because that's what will be more similar to what you're doing in calculus. Now, as we said on Thursday, this is a particularly challenging problem for us because we can't just split the derivative because it's a second order differential. So we can't use the tools that we had first semester. What you have to start doing is start reading what the differential equation is actually telling you. So I will solve this for the differential because we're going to need it expressed this way. So I'm going to write the second differential by itself. I'm going to divide both sides by m and have minus k over m times x. In the past, when we've had a differential equation, we've not really talked about what it means. Today, in your verbiage, in your notes, there are some things about the way you should say this that I think matter. This expression is what calculus is really about, and why I think we don't do calculus very good justice. Calculus is a set of tools that's supposed to be designed for you to be able to take differential equations. It is differential equations that really makes up the backbone of most science, not calculus. So calculus is why you learn things like multiplication and division before you take algebra. You have to know the basics for how arithmetic works because algebra is an abstraction of arithmetic. Instead of 2 plus 2, it's x plus y, so we've added every number together. Calculus is a relationship between functions, and differential equations is how those functions are related. This is what's being stated here. Calculus is the backbone for how you do the arithmetic portion of a differential equation. But you have to have an understanding of what's being said here. This is not an equation on its own. It's telling you how two equations are related. It says if you have an equation about x, when you take the second derivative of that equation, you get back the first equation times a constant. That's what this says. It's saying the second derivative of this function produces a constant, produces a negative sign, and produces the original function. Now on Thursday, we tried a function that didn't work. If you'll remember, we tried x equals x naught e to the minus ct. I usually try to steer my students to bring up this particular function because in calculus, you've learned that the derivative of the exponential is just the exponential. And since this function produces the same function after you take the derivative, it's a good place to start. Now, for those of you who don't remember this, when you take the derivative of this with respect to t, you just get minus c e to the negative ct. That's the first derivative. So if I say, what is dx dt of my function, that would be dx dt. And if I take the derivative again, I just get that repeated. This is what we did on Thursday. If I do the work here, this just becomes x naught c squared e to the minus ct. And if I reorganize it, c squared x naught e to the ct, I want you to see that that is the same function that we started with. This is close. In fact, if I substitute in, I'd be able to say d squared x over dt squared equals a constant c squared times x. It's close to that, but obviously what's missing is the negative sign. And it's the negative sign that's crucial here. As we discussed earlier, the negative sign is what makes this a restoring force. So our differential equation has to produce a negative sign, not on the first derivative, but by the second derivative, which is why we said this function doesn't work. And what function do we say does work? Sine or cosine. Either one of those will work. And again, this is where I want to slow down as much as possible so those of you who don't have calculus can pay attention to this. You need to know how to do this. We're going to take a look at both of those functions for just a minute. We'll start with x and deal with sine. We'll say x is a function of t equals x naught sine ct. I'm just putting a c here. I need some constant because we know this has to produce a constant. And so I'm writing this as our basic equation. The x naught is here because it represents our amplitude. The sine is here because we know the object travels back and forth between the amplitude. So sine makes a good choice for us to start with. E never made a good choice because our object does go back and forth. It doesn't just slowly decay and go away, which is what e to the negative ct would have done. So this would have been a good starting point from the beginning because we know that sine functions go back and forth all the time. But we also know that cosine functions do the same. So both of these functions are reasonable choices. You need to know how the derivative of these functions work. And so this is something that you just need straight memorization. Just memorize this, please. You need to be able to do this. I'm going to do the first derivative for both. So this would be us taking our function and taking just the first derivative. The x naught persists because it's a constant. The derivative of sine is cosine. So this becomes cosine ct. But there is something that you guys aren't aware of called the chain rule. You guys in calculus do know the chain rule. So you know that the derivative of sine t is cosine t, but there's a constant here, so you have to do another derivative of what's inside the parentheses. This is something called the chain rule. And if you take calculus, you'll learn it. I don't care if you learn it or not. All this does is pop out a constant. So it pops out the c. That's all it does. So that makes this c times x naught cosine ct. The derivative of cosine is going to be almost exactly the same, except the biggest difference is that when you take the derivative of cosine, you get minus sine. I'm not going to rewrite all of that, but minus c x naught sine ct. It's the only real difference. Now, I know for you guys who are in pre-calc, you've begun to do some work with sine and cosine functions. I've seen it in the homework, graphing of sine and cosine and tangent functions. You are aware that cosine and sine are a 90-degree phase shift of each other. You're aware of how phase shifting works, and you understand that inside this parenthesis, it could be more complicated, right? It could be CT plus a phase shift. You guys are familiar with all of that. We are not doing anything with that, and we won't have to know those kinds of things. It is expected, however, that you could, when we are done, be able to sketch a sine or cosine function without a phase shift. And I'm also expecting that you know how changing this variable changes the wave function, knowing whether it spreads it out or makes it smaller. You should know that. So that's what you're learning in pre-calc. I should be able to count on that prior knowledge. You guys who all have calculus should already know that. So am I good to assume that those are things you remember? You can always just plot it in your calculator and change the value for C and see how it affects the answer. So be using your tools. So take the derivative again, because we don't care about the first derivative, we care about the second derivative. So I'm going to take the derivative again. Since it's going to pop out another constant, it's going to be the same constant, so you just get squared. And since the negative sign is already here, it persists, because the derivative of sine doesn't produce a negative sign. So whether we start with the sine function or we start with the cosine function, in the end, this function matches what we had before. The difference is that here x is x naught sine ct, and here x is x naught cosine ct. We now have two candidates that produce the desired results, because our function was negative k over m x equals the second derivative. This has to be c squared. Now, I want to stop here because it's a lot. Move this to the center. One of these choices is a better choice for our function. They both behave identically, and all we did was guess at an answer so far. It's not like we used some kind of fancy math to come up with this. We just guessed at which kinds of functions can do this, and we have two candidates that we can use. Anybody in E&M knows the answer to this, but you guys who aren't, one of these is better to use than the other. And it's not obvious which is which. It really depends on your circumstance. Depending on how your system starts into oscillation determines which one of these you would choose. But for us, anybody hazard a guess which one we should use, cosine or sine? Why would we use cosine over sine?
Because it would start at it would start with the displacement.
That's right. That's why we would use cosine. At time equals 0, cosine is 1, which means that our object starts at x naught. That's why we would use that one. So it's about where the object starts. It's about our boundary conditions. And our boundary conditions said at time equals 0, the velocity was 0, and the object was at its initial displacement, the amplitude. So cosine is a better choice for our functions for an object that was displaced and started from rest. Hear all of that. You need all of that in your notes. Cosine is the better function for this situation where an object was displaced and started from rest. So I want to go a few steps further. We all okay so far? We're going to use this as our basic function. I'm purposely leaving the c out, but leaving a space. In our work, we found that the second derivative equals minus k over m times x. Our base function looked like this. And when we did our work, we got so we get this from Newton's second law. We get this from guessing at a function. Can we all kind of see that the c must be equal to, c squared must be equal to k over m? Which means in here, c must be the square root of k over m. This is the motion equation for an object that is in simple harmonic motion, started from rest. And it's based on the spring mass. You guys should be able to come up with these two by just taking the derivative. Just following along with the way we took the derivative already. I'm going to help. I'm going to take the first derivative. The x naught stays out. The cosine becomes sine. The inside here stays the same, square root of k over m times t. But now we have to use the chain rule, which brings out negative k over m. And because we went cosine, it produced a negative sign. Cleaning this up just a little bit, my velocity would be equal to negative the square root k over m x naught sine square root of k over m times t. Taking the next derivative to find the acceleration, the negative persists. I'm just going to pull out another k over m, so this will just be k over m times x naught cosine. These are the basic motion equations for all simple harmonic oscillators. They are skeleton equations. They work for all simple harmonic oscillators, every one of them. So you can't use V equals AT plus V naught. This is a motion equation for a simple harmonic oscillator. It has all the properties we talked about. For example, at time equals 0, do you see that at time equals 0, the velocity will be 0? Isn't that what we said would have to happen? But the sign of 0 is 0, so at time equals 0, the velocity is 0. You guys are smart kids, but you tend to miss the forest sometimes. Do you also remember that cosine and sine can be no bigger than 1? Right, you see that also? So if I just move these to the side, x max is when cosine is 1. That's clearly x naught. V max is when sine is 1. I'm dropping the negative sign because it's just talking about how fast it's going. Obviously, it's going to be going one direction or the other through the center. But this has to be the max. Oh, I forgot the x naught. Sorry, x naught. And A max has to be when cosine is 1. All right, that's as far as we can get today. As an example, I want you to consider two different things. I'm gonna try and draw this, but I do a terrible job drawing this, so just give me, I don't know, patience. Okay, it's supposed to be a bowl. Is it kind of a bowl? Would you buy it as a bowl? Okay. Imagine a bowl, right side up, concave up. You put something to eat in there, and take that same bowl, turn it over on the table. If I put a marble here, the marble will roll back and forth inside the bowl. A bowl like this can be a harmonic oscillator. Whether it's a simple harmonic oscillator will depend on what the restoring force is. For you guys who are just kind of new to physics and didn't have AP Physics 1 last year, this would be probably a difficult sounding problem because you would have to know how steep the bowl is. But can we all buy in that the steepness of the bowl is changing? So there is some proportionality here that is similar to a, maybe not linear, but the force is getting bigger, trying to push it back towards the center every time. And equilibrium would be at the bottom, right? If I just put the marble at the very bottom of the bowl and let it go, it wouldn't go anywhere, right? It would just sit at the bottom of the bowl. That's a clear equilibrium position. A small displacement of the marble causes it to oscillate. All agree? The marble will go back and forth inside the bowl. That is the crux of having a negative sign in Hooke's law. That's what that means to have the negative sign in Hooke's law. So any displacement away from equilibrium pushes the thing back to equilibrium. If you don't have the negative sign, you get the bowl here, where it's just been flipped over. I can put the marble here. The marble at the very top will still be in equilibrium, right? Perched at the very top. But if I give it a small displacement, will it stay or will it be pushed back to equilibrium? Having a positive sign here means that the force gets bigger, pushing it away from its equilibrium position. This would be considered an unstable equilibrium, this one, an unstable equilibrium. This is a stable equilibrium. We build buildings based on stable equilibriums. You push on a building, the wind hits a building here in Tampa, the building sways in the wind. There is a restoring force on the building to push it back towards equilibrium. You can understand why you wouldn't want this to be a restoring force, right? If you push the building a little bit off center, there's a force to keep pushing it off center. That seems like a bad way to build a building. So when we talk about restoring forces and why they have value, we study them because we build most of our structures with a restoring force in mind.